Hi there, everybody. Like I said, I'm going to start doing some more of these practice videos just to show you some examples too. That was one of the things I heard on the survey results. So you'll start to hear and see me a little bit more often on videos to give you some guidance. But again, if you have questions, certainly ask. So this particular problem is similar to one of the ones that's in section 1. It's called, we'll go through this. It says let k be a natural number. And this time we're going to perform the Euclidean algorithm on the two numbers a equals 6k plus 11 and b equals 2k plus 3. So we're not looking at a specific number this time. We're looking at kind of the two numbers that have a particular form to them. So the question, we have two questions that we want to answer. How many steps, how many divisions are needed to get to that zero remainder? And then, like I said in my previous video, we jumped the gun and said, hey, we're also talking about the greatest common divisor here. So what would that particular value be? So there might be a temptation, and this is okay, and I've mentioned this to a few of you as I've talked to you, is that the temptation is to just plug some numbers in for k and then just do it that way. So we could do that, and let's go ahead and just for the sake of argument, let's say that k equals 4, okay? So in that case, I can 6 times 4 plus 11, that means a is 35, and 2 times 4 plus 3 means that b is 11. So we could go ahead and perform the Euclidean algorithm on this. So going through the steps, I'm going to start off with 35 equals, let's see, 3 times 11 will give me 33, and I'll have 2 left over. 2 is kind of small, so we're probably not going to take too many more steps. But then I'm going to go ahead and bring down the 11, and so I have 11 now. And now the question is, how many times is 2 going to there? Well, pretty sure you all can figure out that that's probably 5. 5 times 2 is 10, which means we have 1 left over, which probably means we're about done. So I bring the 2 over, 2 times 1 plus 0. So when I talk about bringing stuff over, just a reminder, like what I'm doing is this 11 becomes our new dividend over here. This 2, the remainder, becomes our new divisor. And then the 2 goes here, and this 1 comes here, and so on. Okay, so just kind of a reminder of what I mean by bringing stuff over. I'm going to take that out of there for now. Okay, so to answer our questions then, what we've got is this took 3 steps, and our greatest common divisor was 1, because that's what this is right there. So now the question is this always the case for any value of k? Or was it just the case when k equals 4? So, well, let's go ahead and do the same process, but this time without substituting something in for k. So just put a little bit of a line in there. And so this time I'm going to start with my 6k plus 11 equals, and for the moment I'm just going to put in like q sub 1, because I know there's some quotient there, times 2k plus 3 plus some remainder. Okay, so if we look at this, we want to multiply, what is our quotient? What are we going to multiply by 2k plus 3 to get as close to 6k plus 11 as we can? Well, it might, when you're looking at that, you might be like, okay, q1, it looks like 3 would probably be reasonable, and it does, because then we'd get our 6k, which, because of the k in there, we have this variable, we need to match that up. So we're going to go ahead and do that. So I'm going to go back and erase my q1 and put in 3. So that'll give me 6k plus 9, and so then that looks like my remainder is going to be 2. Okay, and so then again I'll bring my former divisor 2k plus 3 over, and we'll put this on this side, 2k plus 3, and same process, q2. This time we're going to bring the 2 over plus the remainder. So one thing to point out now is, let's change that because we're using a different color. Okay, so this time when we multiply by 2, since I have a k over here, I need my q2 is going to have a k in it, so that when I multiply these two together, I can get an expression that has 2k in it. And that might suggest to you, oh, well, 2 times k will be 2k. So that seems reasonable. So let's go ahead and do that. So I'll take out my Q2, and I'll put in 2k plus 1. So then I multiply that, and I get 2 times, I'm sorry, I meant, okay, there we go. Actually, I meant that to be k plus 1. There we go. That makes more sense. So 2 times k is 2k. And then we have plus 1 times 2, so that's 2. So it looks like our remainder is, oh, that's weird. There we go. It looks like our remainder is going to be 1. And it looks like we're almost to where we need to be, because my next step then is to bring over the 2. And then the question becomes, oh, it's 2 times 1 plus 0. So therefore, we're done, because we have a remainder of 0. That's the goal in this process. It's a nice thing about the Euclidean algorithm. We know when we're done. Okay? So what happened is, well, it looks like we ended up with 3 steps again. And the greatest common divisor is 1. But what we found out this time is that it doesn't matter what k is. Whatever k we pick, it turns out it'll take 3 steps, and our greatest common divisor will end up being 1. So what we did in the first case kind of gave us a sense of it. Now, I'm going to leave it open and let you think about, do you think that's always the case, where if we do it with a number, we're going to always have the same when we do it in general form? I'm going to leave that for you to think about. Okay? Hopefully that helps, and we'll see you later.